Very well. Objectives. Derivatives. So what we learned so far? We start talking about functions, f of x and y. Then we define the domain of the function. Then we talked about the range of the function. After that, we said, hey, let us talk about the limit, especially the limit at troubling points, like the origin. We talked about continuity. And now we're going to talk about the derivatives, rate of change of the function. So as you can see, they have functions in one variable. We talk about the domain, range, limit, continuity, derivatives, and we talk about integral of the function. We're doing the exact same thing for functions in 2, 3, and more variables. Now, officially, we define the derivatives of function f, x, and y with respect to each of those variables by using the limit definition. First of all, recall that. Let y equals to f of x be a function. This is what you learned in elementary calculus. The derivative of the function is defined as the limit of f of x plus h minus f of x divided by h while h goes to 0. This is the official definition of the derivative of the function. If the limit exists, then you say that the derivative of the function exists. If the limit exists, we can apply those shortcuts that you learned before. We can apply the shortcuts. Well, so I expect you to ask, now that you have a function in 2 variables, how do you define the limit definition of derivative? Now, for z equals to f of x and y, we define not just a derivative, partial derivatives of the function. The partial derivatives. So remember that for the derivative of the function, you have df to dx. Now that you're using partial derivative, we're going to change this symbol and we're going to tilt it a little bit. Partial derivative of f with respect to x is defined as the limit. So again, we have the limit definition of the function. Let us add the point like a and b equals to the limit of f of a plus h and y. So your y is replaced by b. So let's write down b here, minus f of a and b divided by h as h goes to 0. If this limit exists, we have partial derivative of f with respect to x for points a and b. with respect to x. With the same logic, we can define the partial derivative of f with respect to y at this point. So partial derivative of f with respect to y at a and b is the limit definition. Let's get back to elementary calculus. This is the very first definition about derivatives that you learned before. Remember, you had to spend minutes trying to simplify after you plug in x plus h into the function, and then if the limit exists, you said that, hey, the derivative exists. So this is going to be the limit of f of a, comma, you're going to replace y by b plus h minus f of a and b divided by h as h goes to 0. After simplifying this limit, again, if the limit exists, you say that, hey, you have the partial derivative of function with respect to y at a and b. If this limit exists, then we say that f has a partial derivative with respect to y at a and b. Perfect. Well, example. Question says, find the partial derivatives of function z equals to f of x and y, which is defined as x squared y to the fifth. Well, take a look at your function. This function is a nice function. This is a polynomial or nice function. It means that the limit definition is defined everywhere. We're not worried about the limit definition. Well, how do we take the derivative then? Recall. We are getting back to elementary calculus. Suppose f of x is given to you as 2x squared. What is the derivative of the function? You all know that, perfect. So the derivative of this function is 2 times 2 times x, or the derivative of the function, as you all know, is 4x. What if I give you this function? F of x is defined as ax squared. What is the derivative of the function? A is just a constant, it's just something there. So this is going to be 2ax. This is exactly that you're going to do here. To take the partial derivative of f with respect to x, we fix variable y. We fix y. What do I mean by that? We take y as just something that is fixed, a number. It doesn't play any role when you're taking the partial derivative of f with respect to y, with respect to x. So the partial derivative of f with respect to x is equal to 2x. And this is your a. You're just going to copy it down. Y to the first. To take the partial derivative of f with respect to y, we fix x. We fix x. So x is fixed. It means that it doesn't have any role in taking the derivative of f with respect to y. So the partial derivative of f with respect to y is equal to, you copy down your x squared. You're taking the derivative with respect to y, which is 5y to the 4th. Well, let's go over more examples. Another example for you. Find the partial derivatives of the following function. Here you have z, or f of x and y, equals to sine of x divided by 1 plus y. Very nice function. You need some information from elementary calculus. Again, sine function is a nice function. The limit derivative exists, so we're not worried about the limit definition. We call from elementary calculus the derivative of sine of ux. We have to use chain rule. It's going to be the derivative of u times cosine of ux. If you have ux divided by vx, let's see, it's going to be u prime times v minus u times v prime divided by v of x to the second power. These are the things that we need from the elementary calculus to be able to find the partial derivative of this function. So when we are taking the derivative, partial derivative with respect to x, it means that our y is just a constant, just a number. Think about it this way. Here you have sine of x divided by 1 plus a. Just this y actually acts like a constant. So when you're taking the derivative, this is, you're going to apply the chain rule. The derivative of x divided by 1 plus a is going to be 1 over 1 plus a. And the derivative of sine is cosine. So we're going to copy down whatever is in our parentheses. So partial derivative of f with respect to x, you can write it as f sub x as well. So another notation for you is going to be 1 divided by 1 plus y times cosine of x divided by 1 plus y. So think about it this way. You are taking the derivative of sine of a number like a divided by 1 plus y. You have a number divided by 1 plus 1. So we have to take the derivative of a divided by 1 plus y and multiply that by cosine of A divided by 1 plus Y. So A divided by 1 plus Y, the derivative times cosine of A divided by 1 plus Y. And how do we take the derivative here? You can apply the quotient rule, or you can say that, hey, this is just a number. I can write this number in front of 1 plus Y to the power negative 1. Then take the derivative and multiply that by cosine of A over 1 plus Y. This is actually negative A1 divided by 1 plus Y squared times cosine of A divided by 1 plus Y. But in this case, we are taking the derivative, partial derivative with respect to Y, or f of Y, which is equal to, so negative A, negative X, over 1 plus Y squared times cosine of X over 1 plus Y. As you can see, we are getting back to elementary calculus. We need to refresh our memory about using the techniques that we learned before. Well, now I expect you to ask, you took the first partial derivative of the function. Can we take the second partial derivative of the function? Yes, of course. Recall that in elementary calculus, you have just one variable. And you keep taking the derivative of the function with respect to that variable. Like if you have, recall, if you have y equals to a x to the fifth, you could say, hey, the first derivative of the function is 5a x to the fourth. The second derivative of the function is 28 x to the third, and the rest of them. You have the exact same thing with partial derivatives. You can keep taking the derivatives of partial derivatives. But note that here you have two variables. So, second partial derivatives. You have function z equals to f of x and y. Okay, so we can take the first partial derivatives this way. Partial derivative of f with respect to x, or f of x. We can take the partial derivative of f with respect to y as well, f of y. So now I can take the partial derivative of this function with respect to x and also with respect to y. So here you have the second partial derivatives this way. For this guy, I have two partial derivatives. So here I can take the partial derivative of f with respect to y, and I'm going to write it here. And I can take the partial derivative of f with respect to x, again with respect to x. The same here. I can take the second partial derivative of this function with respect to x, and also with respect to y. So I'm going to use a different color so you know that we took the new partial derivative. So the way that you can represent this, it is partial derivative of with respect to y of partial derivative of f with respect to x. This can be written as the partial derivative with respect to x of partial derivative of f with respect to x. The same here. We have partial derivative, the second partial derivative with respect to x of the partial derivative of f with respect to y. And here you have the second partial derivative with respect to y of first partial derivative with respect to y. So you can define 4 second partial derivatives. The first one, the second one, the third one, and the fourth one.